You've been told that high LDL cholesterol coats the inside of blood vessels in much the same way that a drain gets clogged by fat. And this is just absurd. High LDL cholesterol levels are in fact associated with longevity. The overwhelming finding of this systematic review of 19 cohort studies with more than 68,000 participants found that people with higher LDL cholesterol levels lived longer. Let's take a look at exactly what LDL is. It's a complex molecule comprised of both lipids and proteins that the body devotes a lot of resources to producing. And cholesterol, often referred to interchangeably and incorrectly referred to interchangeably as LDL, is in fact only one component of LDL. It's both carried as cargo internally and dotted through the outside membrane. So it's clear that LDL is not the same as pure cholesterol. The fact is, however, that LDL particles can be found in atherosclerotic plaques. So does that mean LDL causes atherosclerosis? No. Just because two factors coexist doesn't mean that one causes the other. The fact is, as shown by this paper, 75% of patients hospitalised with heart attack have normal levels of LDL. Rather, we've got compelling evidence that the root cause of heart disease is actually this: a blood clot, or more specifically, thrombosis. Essentially, atherosclerosis is the result of blood clots forming inside blood vessels. To begin with, red blood cells contain a chemical that is unique to them and only to them, called glycophorin A. And this chemical is not found in any other tissue in the human body. And yet, scientists have been able to prove the presence of this chemical, and therefore red blood cells, by using a stain. And they've found it deep inside atherosclerotic plaques. Of course, blood clots are not just made of red blood cells. They also contain platelets and fibrin, which forms the strands that bind the clot together. And these too have been found buried deep inside atherosclerotic plaques. And the lipid heart hypothesis does not explain this at all. Now, one interesting thing about these clots is that they can occur episodically, over time, one on top of the other. And this then leads to a prediction that atherosclerotic plaques might actually form in layers. And indeed, that is exactly what we find. Here's an example of a single layer plaque that contains a lipid-rich core that's covered by a thick, fibrous connective tissue cap. And here's an example of a plaque with two distinct layers, separate fibrous caps being clearly visible. Hang on, you might say, what about cholesterol-like crystals that we see in plaques? Where does that come from? Well, it doesn't come from LDL. First of all, understand that the LDL in atherosclerosis is contained within things called foam cells. And these foam cells are formed when macrophages ingest damaged LDL. These foam cells store cholesterol that is bound together with fatty acids. And when you bind cholesterol with fatty acids, it makes it form a droplet. And they'll remain in a droplet even if it gets released from the macrophage. It won't form a crystal. The thing is, the cholesterol found in foam cells cannot and does not lead to the crystalline deposits that we see. Red blood cells, on the other hand, can. Their outer membrane contains more free sterols, including cholesterol, than any other cell in the body. And not surprisingly, they're abundant in blood clots. This paper not only describes the central accumulation of red blood cell membranes within atherosclerotic plaques, it details how by injecting red blood cells into animals, investigators were able to produce atherosclerotic plaques containing both cholesterol crystals and LDL. So thromboioclots can elegantly explain the constituents of atherosclerosis. I'd like to now take a closer look at the so-called cholesterol crystals themselves. So understand that you're not actually looking at cholesterol crystals here. but rather the spaces where they used to be before they got dissolved in processing. That means another compound that forms crystals of the same shape could actually lead to the same appearance. Enter phytosterols, which is plant versions of cholesterol which are almost identical to cholesterol. These too can form crystals, crystals which are difficult to differentiate from cholesterol crystals. And phytosterols can be easily delivered by red blood cells, given that they are carried also in red blood cell membranes. And while foam cells don't release cholesterol in a form that makes cholesterol, they're only too happy to release these plant-based cholesterols in a free form that can. So at this stage, it's probably not going to surprise you that phytosterols, this fake form of plant cholesterol, is readily detected in atherosclerotic plaques, and that's been shown by numerous research. This is a case report of a 33-year-old male with premature severe atherosclerosis. And when they biopsied his aorta, they found phytosterols, plant sterols. Fortunately for most of us, our bodies can reject most of the plant sterols that we consume, with only about 1% actually being absorbed and assimilated into our tissues. Some people aren't this lucky, however. They have a disease called cytosterolemia, and that means that rather than absorbing only 1%, they can absorb between 15 and 60%. And the consequence of this can be dire. There being one case of a 5-year-old dying from sudden cardiac death related to premature atherosclerosis. Premature severe atherosclerosis is the norm in this condition where you absorb too much plant sterol. Despite this, phytosterols are often lauded for their ability to reduce cholesterol levels. And we have products like this which deliberately contain added plant sterols which are promoted for cardiovascular health, despite there being approximately zero evidence of cardiovascular benefit and plenty of evidence of harm. And this is, I believe, why seed and vegetable oils need to come into the conversation. All these oils contain significant amounts of plant sterols, even olive oil. And it's the plant sterol content of these oils which underpins their lowering of cholesterol in the blood. With this in mind, can you predict what the effects of each of these fats would be on LDL levels? Now, while olive oil and coconut oil are technically not seed oils because they're made from flesh, they're basically the same. They still contain plant sterols. So this study looked at the impact of butter, olive oil, and coconut oil on cholesterol in the blood. And it found that both coconut and olive oil caused a drop in LDL levels, in my opinion, due to the plant sterol content. And this was despite the coconut oil containing 94% saturated fat. It still led to a drop in LDL. This is a clear repudiation of the claim that saturated fat increases LDL. Now, one of the major reasons seed oils contribute to atherosclerosis is that their polyunsaturated chemical structure contains unstable bonds which are prone to oxidation. Basically, all the seed and vegetable oils you see in stores are oxidised. Fish oil too. This study, for example, found that oxidation of walnut oil occurred within days. And when oxidised oils are consumed, as we often do, oxidation products get absorbed into the body. The more oxidised the oil, the higher the level of blood oxidation products. And the story for blood oxidation products becomes even more interesting when we have subjects with poor blood sugar control. The two left columns represent subjects with normal blood glucose levels, and the right column, those with poorly controlled diabetes, meaning they've got high blood sugar levels. And you can see the blood oxidation product level is much higher in the poorly controlled diabetics. Furthermore, the blood oxidation products lasted for 9 times longer in these subjects, being detected in the circulation for 3 days, compared to 8 hours for the healthier subjects. So what you might ask is the problem with oxidation products in the blood? The answer is atherosclerosis. as in oxidative stress in the blood triggers blood clotting or thrombosis, which, as you now know, is the source of atherosclerosis. In the words of this paper, oxidative stress is involved in all of the major processes involved in the development of thrombosis. So we're now starting to understand why thrombosis happens. So what actually is oxidation? Well, it's basically an umbrella term that refers to a chemical reaction where an electron is ripped away from a molecule. Basically what rusting is. And because of this reactive tendency, oxidation products in the blood can trigger clotting. Of course, seed oils are not the only source of blood oxidation products. Pollution is a major one. And when we inhale pollutants, if they're small enough, they can pass through the blood vessels, the membrane of the blood vessels, coursing through our lungs and enter our circulation. And this has been proven by research that detects pollutant particles in the blood within 1 minute of inhalation. This is why smoking increases heart disease risk, as in the case of President Eisenhower, who smoked 2 to 3 packs a day. Of course, some pollutants are worse than others. Do you remember leaded petrol? Some of you are old enough. It used to fill the air with lead for us to inhale. Well, lead is particularly potent at contributing to oxidative stress. Lead atoms are just the right size to enter the circulation after inhalation. And this study from 2018 concluded that 1 in 6, or 18%, of the 2.3 million deaths every year in the United States is attributable to lead. And remember, it all comes back to oxidation products in the blood. But just how exactly does oxidation get carried around in the blood? What does it actually look like? Well, how about an LDL particle? Hang on a second, I hear you saying. Didn't you just tell us that LDL wasn't dangerous? Well, yes, I did. And on average, that's true. People with high LDL levels do tend to live longer. But LDL particles can become oxidised when they react with other oxidised substances. So you see, normally in the blood, there's a single population of LDL in a normal distribution, which you can see shown here in yellow. This LDL won't harm you. The size and density of LDL, however, changes when it becomes damaged, of which oxidation is a major cause. In this sample, you can see 4 distinct populations of LDL, exactly 3 more than normal, representing the presence of oxidised and therefore damaging LDL particles. This LDL is often referred to as small dents, given they become microscopically smaller. And while most people who have heart attacks have normal total levels of LDL, there being no difference in LDL levels with or without a heart attack, when we look at damaged or oxidised LDL, it's a different story. Look at the level of damaged LDL in the group on the left, who don't have heart disease. Compare it to the oxidised LDL level in the 2 groups on the right who do have heart disease. An oxidised LDL, or of course any other blood oxidation product, is also able to damage this furry layer that lines blood vessels, called the glycocalyx. This is perhaps the most important level of protection against atherosclerosis that most doctors have never heard about. Amongst other things, it shields the artery walls from coagulation particles, secretes something called antithrombin 3 that inhibits clots from forming, and stimulates the production of nitric oxide, itself another potent inhibitor of blood coagulation. The fact that oxidised LDL damages the glycocalyx means it significantly increases the risk of clotting and therefore atherosclerosis. Oxidation stress too appears to be the cause of calcification within arteries. Oxidation's been shown to lead to DNA damage, which leads to the expression of a chemical moiety called poly-ADP ribose. And this then lays down calcium within the lining of the arteries. That coronary artery calcification is associated with unstable plaques and heart attack is therefore probably not a coincidence. Interestingly, statins are also known to damage DNA, a fact which was apparent to the Japanese scientists who stopped researching the mycotoxin that eventually became the first statin because of the increased rate of cancer in test dogs. Which makes it unsurprising that statins also significantly increase coronary artery calcification. Now, this ties in with the most common cause of sudden heart attacks, which is not the presence of atherosclerotic plaques themselves, but rather their rupture. High calcium scores indicate an increased tendency for plaques to rupture. And while atherosclerotic plaques themselves can narrow arteries, the narrowing is usually incomplete, restricting but not obliterating the flow of blood. This then affords time for something called angiogenesis to occur, or the creation of new blood vessels. Essentially, when blood vessels become too narrow to carry the desired volume of blood, new blood vessels can be formed that act as a detour around the restriction. In the case of the rupture of an existing atherosclerotic plaque, the resulting thrombus, however, that forms can be so large that it suddenly and completely occludes the vessel, with no time for angiogenesis to occur, and this then results in a heart attack. So then we'd really want to know what factors are involved in the stability of plaques, what factors might lead their tendency to rupture. And this depends mainly on the integrity of the fibrous cap of connective tissue, shown here by the yellow arrow. And with such a thick cap, as you see here, we can tell that this plaque is stable. Compare it to this plaque with a thin fibrous cap. This plaque is at high risk of rupture. The question is, what causes this cap to thin out? And I believe the answer comes back to foam cells that hold the oxidised LDL. Remember, the foam cells don't take in healthy LDL, they only take in the damaged or oxidised LDL. So macrophages that have ingested this oxidised LDL secrete enzymes that break down this protective layer, the fibrous cap. These are called matrix metalloproteinases, and these enzymes have been independently associated both with the tendency of plaques to rupture and cardiac mortality. Oxidised LDL clearly plays a role in the secretion of matrix metalloproteinases from these foam cells or macrophages. Now, as an aside, the presence of oxidised LDL is quite reliably associated with something called the triglyceride to HDL ratio, there being robust evidence that a low ratio is associated with a low risk of cardiovascular disease. And this is something that can easily be assessed on a standard blood lipid panel. There's another elephant in the room here, though, when it comes to heart disease. Diabetes, which is associated with a tripling of deaths from heart disease and stroke. High levels of sugar in the blood are so problematic has been known for a long time. This research from 1962 demonstrates glucose abnormalities in 73% of heart attack patients. And again, the mechanism is oxidative stress. Both high and especially fluctuating blood glucose levels generate oxidative stress at the level of the mitochondria, the consequences of which you saw earlier when combined with seed oil consumption. A very good reason to keep your blood glucose down. The premise that oxidation is a major cause of heart disease is that antioxidant supplements might be beneficial. And indeed, the antioxidant N-acetylcysteine has been found to be protective against heart disease, as has the antioxidant coenzyme Q10. I'd like to now circle back and finish off the discussion about seed oils. And I believe the evidence of harms from seed oils are now convincing enough that we should be all discouraging their consumption. The consumption of seed oils began to rise in the early 1900s, well timed to have a causal role in the heart disease epidemic. And it's not just this association that suggests their consumption is problematic. 4 randomised controlled trials, the gold standard of research, have demonstrated the harm of consuming these seed oils. In this study from 1965, patients post-heart attacks were randomly allocated to one of 3 groups. There were 2 intervention groups consuming either olive or corn oil, also recommended to reduce their saturated fat intake, and a control group on a regular diet. After 2 years, 75% of the subjects in the control group remained free of repeat heart attacks, compared to 57% and 52% of the olive and corn oil groups, respectively. Hardly a ringing endorsement for olive or corn oil. The conclusion of the investigators was quite blunt, in fact. Corn oil cannot be recommended in the treatment of ischemic heart disease. And in my opinion, this study also raises questions about olive oil. The Sydney Diet Heart Study was a randomised controlled trial examining the effects of replacing saturated fat with polyunsaturated fat in men who'd had heart attacks. But despite being finished in 1973, the results on whether this intervention reduced cardiac mortality were destined to never actually be published. It was only after Dr. Chris Ramsden uncovered the raw data on punch cards and magnetic tapes buried in a basement that the full results were eventually published some 40 years later. The key finding being that the increased intake of polyunsaturated fats, as found in seed oils, increased the risk of death by 62%. A similar story exists for the Minnesota coronary experiment, which also finished in 1973. Remember, this was just before the food pyramid came out. If these studies had been published, do you think we would have ended up with the food pyramid the way it was? It would be madness. It was a double-blinded, randomised controlled trial on more than 9,000 men and women, again evaluating the effect of increasing dietary polyunsaturated fats. And again, there was an inexplicable delay in publishing the full findings. It took 16 years to just publish a few redacted findings. And when the results were finally published 43 years later, again after the raw data was located in a basement, it was revealed that increasing seed oil intake increased the risk of death, a result that was knowingly hidden for decades. And when the now deceased lead author was asked about this delay of publication, he explained it was because the study results were disappointing. More recently, we've got the Women's Health Initiative study. So published first in 2006, it was a massive study of over 48,000 females designed to definitively assess the benefits of lowering saturated fat and increasing polyunsaturated fat intake. The most important outcome of this kind of study clearly being survival. And while the results were technically published, they were done in a very obscure manner, almost like the authors didn't want anyone to actually see them. This vague sentence on page 661 of the publication was the single reference to the only statistically significant finding within the whole paper. Remember, this study cost $700 million US, and that was the best they could do. The finding being that females with a history of heart disease faced a 26% increased risk of complications like heart attacks if they followed the intervention diet. Furthermore, the most recent published data demonstrates that the risk of the low-fat intervention group increased over time to between 47 to 61%. And interestingly, in further subsequent publications, they've now stopped publishing that data altogether, even when you go through it with a microscope. You may now be questioning the widespread promotion of seed oils as healthy. And in my opinion, you should. The problem is we're consuming a huge amount of seed oils. This BMJ paper found that seed oil intakes exceeding 6% of total energy are more harmful than high-carb diets. The fact is Australians consume more than double this amount, deriving 13% of their energy from seed oils. The fact is we'd be much better off with animal fats. In closing, I'd like to acknowledge the work of Scottish GP Malcolm Kendrick on exposing the role of blood clots in atherosclerosis. He's the author of this book, which provides an excellent summary of the clotting theory, and is also the subject of cancellation or deletion by Wikipedia, accused and convicted by online editors for being a fringe figure who had the absolute audacity to argue against the lipid hypothesis. Thank you.